And the majority of content is coming from this textbook, Computer Networking book, which is a very popular networking textbook for many universities to use. Okay, for networking, so first is the layered structure for the internet. And internet most people, they will classify the internet layers into this 5-layer structure. The international standard is more than 5 layers, is about 7 layers. Basically, in the international standard, application layer was divided into three layers. But majority people in the networking field, they think that the top 3 layers, they are too similar to each other, and they should all be classified into one layer called application layer. Basically, application layer means all the networking software. So you can think that networking software is about application layer. So when you generate a networking software, like when you generate a voice over IP program, when you generate a social networking app, then whatever you do on the software design, on this software programming, is about application layer. And in your application layer, you basically use all the available resources provided to you by the operating system. So application layer is about programming, about software apps or program running on top of OS. All the bottom layer, all the 4 layers below, they are provided by the operating system and the physical computing device. So that is application layer. Transport layer is in charge of delivering data from one host to another host. So that is called transport layer. The protocol used in transport layer is called TCP and UDP. So dominant protocol is TCP. So most data service applications, they use TCP for that. And some real-time multimedia application, they rely on UDP for that service. Network layer is about internet routers, and basically it's about how do you find the route for you to deliver the data from one end to another end. This transport layer, network layer, they are closely related to each other. I will explain a little bit more later about these 2 layers. The link layer is also called data link layer. So either people call it a link layer or people call it a data link layer. Data link layer is about data transfer on one physical medium. So this transport layer, network layer is about internet delivery. That data is going through many devices on the internet, so it can be delivered through a long way across the country, across ocean. But data link layer is about data delivered on one physical medium. like on the Wi-Fi. So on one Wi-Fi hotspot, every data is delivered on that wireless link through that Wi-Fi router. So that is called the data link layer. When the data goes through the Ethernet line, that is another data link layer. So Ethernet line is another data link layer. You can think that data link layer is about data transferred in one hop between one computing device to the next computing device. The transport layer, network layer, is about data delivered through multiple hops through the entire internet. So the data will go through multiple hops. So for data link layer, the protocol could be very different depending on that physical medium. Like on Ethernet, it will use Ethernet protocol. On Wi-Fi, it will use a Wi-Fi protocol. On the Bluetooth, the data is delivered following the Bluetooth protocol. So different data link layer, their protocol could be very, very different because of the unique feature for each physical medium. They could be very different. Like Zigbee, Zigbee is mainly used in the industry, like in the mine industry. They have used Zigbee for a long time. Zigbee is compared to Wi-Fi, it's similar to Wi-Fi, but compared to Wi-Fi, Zigbee has much slower speed, so it's very slow. But Zigbee transmission could be longer range and it's more reliable. So in mining industry, many mining industry, they use Zigbee because the signal can travel through tunnel, through many obstacles without much problem. Bluetooth is much shorter. We all know that the transmission range for Bluetooth is much shorter. And also data rate is slower than Wi-Fi. But Bluetooth is very energy conservative, so it's very energy efficient. It's not like Wi-Fi. So Bluetooth headphone, you can use a Bluetooth headphone for 8 hours without any problem. The bottom link is the physical layer. Physical layer is about the bits on the wire. So physical layer is basically if you learn electrical engineering, then electrical engineering on the communication part, you are dealing mainly about physical layer. How do you transmit bits information on a physical medium? How do you encode that information? This is 0, 1 bit information on that physical medium. What kind of spectrum do you use? How do you generate that physical medium in a more efficient way with more robustness to the noise? So all those designs, they are related to the physical layer. So these are the 5-layer structure for the internet. And for networking, everything is about this 5 layers structure. And in the internet, the data generated by computing device. Of course, right now, it's the computing device is much more broader than computer or desktop or laptop. It could be any kind of computing device. For example, it's a smart speaker or smart TV. They also treat it as a computing device. When the data is generated, it will go through these 5 layers, one after another. When the data goes through one layer, it will add additional like header and footer to that data to include specific information useful for that layer. So the data will go through application layer, transport layer, network layer, data link layer, then transmitted on the physical links. Then at the other end, the data will go through these layers in the reverse order to extract the information out and deliver to the application. So like a web, email, voice over IP, and all those are like softwares. They are talking about application layer. They all belong to application layer. Transport layer, the dominant protocol is TCP, UDP. Network layer, the only protocol is IP. Because we are on the internet. So current internet interconnected network, the protocol is on IP. And data link layer depend on the physical medium. You could use different protocol. On the copper wire, you could use Ethernet protocol. On the cellular system, you could use cellular's 4G or 5G, their protocol and standard for this data transmission. So internet is basically is about TCP and IP. So people also call internet as TCP/IP because internet is basically the design to connect all the local area network together. Before TCP/IP was designed, there are many local area network exist in government agencies, in some national libraries, in some universities, but they are running their own specific software and hardware. They do not interconnect with each other. Internet was designed by the sponsor, by the DARPA, and the basic purpose is to interconnect all those isolated local area network from the national lab to university to the government agency together to share the information. So internet design is about TCP and IP. It make everything to go together. So data link layer belong to local area network, and internet is about TCP and IP part. Okay, for the TCP, so TCP and IP, TCP IP, they are the essential concept and knowledge for the networking, to understand networking. And you have to understand what header, what packet, this layered information has been added to each data chunk on the network. So when the data goes through each layer, it will add a header in front of the data. That header will provide information used by that specific layers protocol to help to facilitate the data transmission. The TCP header is here. Usually people describe TCP header in this structure, like every 4 bytes is one row, and you have multiple rows, so that is header. TCP header could have variable size, but most TCP header, if they don't have the optional field, then they will have 5 rows here. So each row is 4 bytes. So normally TCP header is 20 bytes. So that's the most TCP packet. Their header is 20 bytes. Some TCP packet, they could have optional header. So then the header will be a little bit longer than 20 bytes. So this is header. Then after header, then this is application data. In the TCP header, the first 2 bytes is about source port number. I will explain what the port number means. And then next 2 bytes is about destination port number. And the sequence number, acknowledge number is try to remember the ordering of this data, because when data transmitted on the internet, they were broken up into many small chunks. Each chunk is transmitted as one packet. So if you transmit like a voice, a music file, the music file could be break up into 100 packet. Then the sender will send this 100 packet out individually to the destination. Because of the complexity of the network, those 100 packet, they could arrive at the destination out of order because they may go through different physical link. So how can the destination, the receiver part, know which packet is first, which packet is second? Because the receiver need to assemble all those 100 packets together in order. So the sequence number, acknowledge number is about that ordering information. And so the receiver will use the sequence number to piece all those different packets together to come back with original data without any problem. So that's a sequence number used. Acknowledge number is used because it's just like when you make a phone call. So when you try to understand networking transmission protocol, you should use telephone call as analogy to try to understand the concept. When you call the other side, if you don't hear any response from the other side, you will ask, can you hear me? Then the other side will say, yes, I can hear you. Or if you're listening to your friend talk, in order for your friend to know that you're listening, you have heard all the content, you should frequently say yes, yes, just some very simple acknowledgement sound, so that your friend can know that you are still listening and communication is still going on smoothly. So acknowledgement is basically for the receiver to tell the sender that how many packets I have received. So that's the acknowledge number used for. This is several bits. I believe it's 4 bits. These 4 bits is show the header length. Remember the header normally is 20 bytes, but some header they could have optional field, so the header could be longer than 20 bytes. Then the header length will tell the receiver how long is the header. There are several bits here that are not used, and in the beginning, when people design TCP header, they want to reserve some bits that can be used later in the future. In the future, when there's new applications, then we can use those several bits. So there are several bits. They were deliberately not used in the design, but right now they are still not used. Here are several very important bits. So each one is 1 bit. So each one is called control flag. This flag is urgent. Basically, the sender tells the receiver that this packet is urgent, and the receiver should do things correspondingly. But most applications, they ignore this bit. This bit is ACK, is called ACK. This means that if this bit is set as 1, that means the information in this acknowledgement number field is valid. Normally, receiver does not need to check what's the value in the acknowledge number field. But if this bit is set as 1, then receiver should check what's the value in this acknowledgement. Basically, the receiver should check the acknowledgement to see how many data has been received by the other end. This is P is called push bit. Push the bit means that when receiver receive this packet has this bit set, receiver should immediately push this packet to the application, because normally the packet is sent and received by a network interface card. So when a network interface card, like Ethernet card or Wi-Fi card on your smartphone, when it receives data, many packets sent from other end, the network interface card will accumulate multiple packets, and then it will put them together and deliver to the application in a batch. So you don't need to create too much interruption to the operating system. But the push bit means that when you receive such a packet, the network interface card program, the driver for network interface card, should immediately push this packet content to the apps, to the application. So that's the push bit used. The reset, the R bit is reset bit. It means that when you receive this reset bit, it means the other end want to terminate this connection. So that's the reset bit used. So when you receive a packet with the reset bit, then you can terminate this TCP connection without any problem. This is the SYN bit, so they are related to connection setup and connection close command. I will explain that in a moment. The checksum is used for the receiver to verify whether the received packet has any bit error or not. Because during the transmission, because of the noise or some other reason, the whole packet may have a few bits that has been flipped, may have a few bits that has wrong information. The checksum is used for the receiver to do calculation to find out whether the packet has any bit error. So that's it's called checksum. And the sequence number, acknowledge number, I will explain a little bit more detail a little bit later. As I said, the network layer, transport layer, they are closely related to each other, but they are different. So from the logical point of view, you can try to use post office mail delivery as an analogy to understand. When you deliver a mail, when you deliver a letter to your friend, suppose your friend living in one specific room in an apartment building. Then when you deliver it, the mailing address will have the mailing address for that building. In addition, the room number for your friend. So you can think that the network layer, the addressing in the network layer is about that building. And the addressing in the transport layer, like in TCP, the port number, is about the room number. So because each computer, you can think that each computer is like a building. So each computer has its own IP address. So each computer has one unique IP address. But on this one computer, you could run multiple networking applications. Like even on your smartphone, you could run multiple network program. Each network program need to accept and send data to the internet. So how do you distinguish these multiple networking program running on the same IP address computer? You use the port number. It's just like in an apartment building. How do you distinguish the person living in one room with a person living in another room? So you use a room number to distinguish them. So in the internet, we use the port number to distinguish different network program running on the same computer. So network layer is logical communication between hosts. The transport layer, this port number, is the logical communication between process, because on a computer, each network application is running in a process. So the port number is trying to distinguish all those running process. For example, we use this as one example. Suppose this computer B and computer D, they communicate with each other. But this computer D is a server. This server is running both web server and email server. Suppose this computer B is a client. The client is connecting to this server D on both the web service and the email service. Then how do you distinguish these two different connections? Remember, for these two different connections, their source IP address, their destination IP address are identical to each other. How do you distinguish them? You use port number to distinguish them. Like the port number 25 means this packet, this connection is for email service. This port number 80 means this TCP connection is destined to the web service. So the server D, when it receives a packet, it uses the destination port to determine whether this packet I should deliver to the web service program, or whether I should deliver this packet to the email service program. So that's how the operating system distinguish and deliver each packet to the correct running process. Just like for main apartment building, the doorman will use the room number to deliver the letter to each person living in this apartment building. Okay, so the TCP is it's called Transport Control Protocol. So that's a full name for TCP. TCP is called Connection Oriented Demultiplex because each TCP connection is uniquely identified by these four values: the source IP address, destination IP address, source port number, and destination port number. So for the addressing, you need to use both TCP port number and also the network layer's IP address for the addressing. So receiving host will use all four values to determine which running process should receive this data packet. So that's how the operating system decide how to deliver the data to each running process. So in this way, two connections cannot mix together at the receiving host because they will different by one or two of this value in these four tuple values. And when a server host support multiple simultaneous TCP connections, then each TCP connection on the server will create a so-called socket, and it may create a child process. Like for example, we use web server as example. The web server will have always running server process listening on the port 80 and port 443. Whenever it receives a TCP connection request on that port, this parent, this web service process, it will generate a child process. This child process just dealing with that incoming request. So this parent process is always running and listening on this service port for incoming connection. Then all these simultaneous incoming connections, they will defer by the port assigned to that service. So for the web service, it's always listening on port 80 and port 443. But when it generates a child process, the child process may run on port 2000. Then for another connection request, the generated new child process, it may run on port 3000. So operating system just give different child process with different port number. So that port number is to use as unique identification for that child process. So whenever the parent process receive a connection, it will use this fork command to generate a new child process. The new child process will deal with this incoming connection request. This fork command is accept command. They are all the socket programming API. Basically, these are the API provided by the operating system to the networking software programming. So TCP header is much more complicated because it is connection oriented, and also TCP provide more service. And UDP, on the other hand, is much simpler than TCP because UDP, it doesn't provide like a retransmission request. It doesn't do acknowledgement to the other end. So it's a very, very simple protocol. So it only has essential information. The port number is still needed because remember, we still need port number to distinguish process. So port number is still needed. But beyond that, UDP only has two information. One is checksum, just for the receiver to check whether the packet has any bit error or not, and the length of the entire UDP, the length of the entire UDP packet. So UDP packet, the packet header is only 2 rows, so 8 bytes. It's much shorter than TCP header. So it's much shorter than TCP head. So from this point of view, the overhead for UDP is much smaller. For even a single byte transmission, if you transmit using TCP, this packet will at least have 41 bytes because of this 40-byte TCP header. But if you transmit it using UDP, then the packet is only 9 bytes because the overhead is only 8 bytes for the header. And UDP does not have this sequence number, acknowledge number, because UDP does not do retransmission request. TCP is like if the receiver find it missed one packet, or receiver find the packet has some bit error, receiver can use this sequence number, acknowledge number to request sender to retransmit that packet. So reliable data transfer, they usually use TCP protocol. So whenever there's a packet missing or wrong, the TCP will handle this packet retransmission. Then in the application layer, when you generate this program, you can just assume that data will be transmitted to the other hand with 100% accuracy. So this 100% accuracy is guaranteed by TCP protocol. On the other hand, UDP does not have that retransmission mechanism. So UDP cannot guarantee 100% accuracy. When the sender sends data out to the receiver using UDP, you do not know how many bytes packet has been lost, or how many packets has bit error that received by the receiver, because it doesn't have that verification mechanism. So UDP protocol is usually used for streaming multimedia application, because multimedia application, they have this requirement. They tolerate loss. So if you transmit voice or video, if there are one packet loss in this transmission, it does not matter that much. Like a voice, it may have some noise. On video, you may have some mistake on the video, but you can still watch the video or listening to the Spotify music without much problem, just to have a little bit noise there. Right? But the communication can still go through. So multimedia application can tolerate loss. On the other hand, multimedia application cannot tolerate this rate. So it's very rate sensitive. So if you miss the packet, then you just ignore it. You want the data to be arriving at the destination continuously without interrupt. So that's why multimedia use UDP. TCP, on the other hand, is used by all the data service, data-based service. Like when you transmit a web page, you want the web page has no single bit error. So data-based service, they do not tolerate loss. They need 100% accuracy. On the other hand, they are insensitive to the rate. So when you transmit a web page, if it transmit in 10 milliseconds or if it transmit in 1 second, it does not matter that much. So it can tolerate slow or high and slow transmission rate. So because of that, all the database services, they use TCP. All the multimedia service, most multimedia service, they use UDP because of this different requirement. And for TCP, as I said, TCP is a connection-oriented protocol, because for TCP, if you use TCP transmit data, you need to establish the connection before you actually send data to the other end. And this TCP connection setup is usually called three-way handshake. Basically, TCP setup need this 3 packet back and forth between the sender and receiver. And that's why it's called a three-way handshake. So in the internet, the basic communication mode is a client server mode. Basically, client send connection request, then the server provide the service. So the majority of internet communication is the client server mode. So the TCP connection setup is initiated by the client. The client will send a packet. It's called a SYN packet, and basically this packet does not have any data. It's just a 40 bytes TCP packet header with a 0 byte on the data part. This packet has that SYN bit set as 1. And so that's why this packet is called a SYN packet. All the other control flag on that packet header is all 0. Remember, these are the control flag in the TCP header. So each flag is just 1 bit. So this packet has that SYN bit set as 1. All the other control bit, they are all 0. And in this packet, the sequence number is meaningful. Basically, the client basically a computer client OS, the operating system on the client, it will randomly pick an initial sequence number to be used for its TCP connection. So the sequence number field will have the initial picked client sequence number by the client operating system. When the server receives this SYN packet on that service port, like on port 80, then the server program, it will send a SYN-ACK packet to the client. This SYN-ACK packet just means that this packet, this control bit, the SYN bit and ACK bit, they all set as 1. All the other control bits, they are 0. So this is called SYN-ACK bit. And in this packet header, the sequence number is randomly picked by the server program, by the server-side program. And the acknowledge number field will be this client sequence number plus 1. So this is used to tell the client that I have received your initial sequence number because I return back that number plus 1. So you know that I have received your initial sequence number. Then the client send another ACK, the third packet ACK. In this packet, the sequence number is basically the client sequence number plus 1. And the acknowledged number will be the server's initially picked sequence number plus 1. So this one will tell the server that I also received your initial sequence number picked by you. Then after this three packet, either the client and server, they can send data packet to the other end. So all 3 packets, they have 0 byte in the content part. All 3 packets, they only have the TCP packet header. So they are all 40 byte packet on the internet. So all 3 packets, they are all 40 byte packets. So remember here, the client sequence number, server sequence number. And you may wonder why I don't start sequence number 0. I always start with the initial sequence number 0. Then we don't need to exchange this information anymore. The problem is that if you always start your TCP connection with a 0 sequence number, then you may have some trouble. You may have some trouble when you act as a receiver side. You may have trouble to distinguish 2 TCP connection from the same client, because all their packet, they have the same 0 value in a sequence number. So you will have trouble to distinguish whether this packet is from this process or from that other process. And you may also have trouble to distinguish whether the packet is a duplicate packet, because sometimes because of network transmissions complexity, a packet may be delivered to you twice because of the network delay and some networking routing issues. And you use a sequence number to distinguish that I have received the same packet before. But if they all picked a zero value in the initial sequence number, then it will create a lot of trouble for that. So that's why for in the TCP design, the sequence number will start from a random value picked by the client, by the sending computer. So 11 now right now is 11:46. Let's take a 10 minutes break, and we will finish the second half of this class. And I will try to finish these lecture slides within this second half of this class. So right now is 11:46. Let's resume the class at 11:56. Okay. I will temporarily halt this recording for this class. Halt recording. Okay, let's resume the class. So let's finish the remaining lecture for this class. As I said, this is a three-way handshake, and three-way handshake TCP setup is very important concept, and because for all the networking management, when you set up firewall, when you set up routers rules, when you do network traffic capturing, TCP connection setup packet is basically a flag for you to indicate the starting of a new network connection. So all the firewall rules, they use this TCP connection setup to determine whether I will allow this connection go through or drop this connection. So these are very important concept. And the TCP connection closed down is using these procedures. Normally, when a client, like when you are using a web browser, when you close your browser or close a tab, your browser will send a packet. It's called a FIN packet. Basically, this packet is a FIN bit. That is one control bit. Is set as 1. All the other bits, they are 0. When the server receives it, server will send 2 packets consecutively back to the client. It will send one acknowledgement packet to tell the client that I have received your connection closed down request. And it also sends the FIN packet back to tell the client that I'm going to close my connection. Then the client will send back acknowledgement to the server to acknowledge that the client will close this TCP connection after this timeout time period. The server will close the TCP connection when it sends out this FIN packet. So it doesn't wait for the acknowledgement to close this TCP connection. This is a normal standard procedure for TCP connection closed down. But there are some other way to close the connection. It's called using the reset packet. So when the client or the server want to close the connection without doing this FIN-ACK polite way, they can simply send the packet with the reset bit set as 1 to the other end. And then you just leave without doing anything. So this reset-based TCP connection closed down, you can think that it's like an impolite goodbye. So normally when you say goodbye through a phone, you will wait for the other end to say bye-bye again, and you may say a few wishing words, then you close the phone call. But if you want to shut down the phone call without that polite way, you can send a reset packet to the other end, then you just leave. this is a list of the common network port number. So when you do network management, when you set up firewall rules, you will actually use a TCP port number to determine what this packet is related to which service. So these are the predefined port number for the well-known service. Like for the FTP, file transfer protocol, the port number is 2021. FTP has been used very popular in the early stage of the internet when you transfer files. Right now, they are not very popular again because web is the dominant net communication way in the internet right now. So all the file transfer, you can use web to finish that, to accomplish file transfer by using the HTTPS protocol. So FTP become less common on the internet. This secure shell SSH is the remote login. The port number is 22. The protocol, normally it use TCP because this remote login, you require 100% accuracy in your data transmission. So by default, they use TCP. But some secure shell, they can use UDP as well. When you use UDP, because you still need to maintain 100% accuracy, so that means your networking software, your programming on the net application layer, you need to do this data retransmission request, data checking by yourself. When you find there's the missing data, you need to request the other end to resend the data. So if you use UDP protocol, your networking programming, you need to take care of data retransmission. But if you use TCP protocol, because TCP protocol implemented by operating system, it can guarantee 100% data accuracy in its data transmission. Then when you generate this networking program, when you do networking programming, you can just assume the data you received is 100% accurate. So, so that's the difference when you use TCP or UDP from this programming aspect when you generate networking software. And what's the difference between using these two protocols? Telnet is basically replaced by a secure shell because Telnet is remote login with using plain text, so no one uses Telnet anymore. Email SMTP is called Simple Mail Transfer Protocol, so it uses port 25. And the DNS is the domain name system, so everyone uses DNS to get the IP address for the English domain name. So it's a DNS, domain name system is port 50. So you should memorize Telnet, this is secure shell, port 22, port 50, and port 80 is for HTTP. And port 443 is HTTPS. You should memorize this port number by your heart because they are so often appeared in the network. So you should memorize them. For some other port number, they are less common, so you don't need to memorize them. If you see a port number that you don't understand, you don't know, you can just Google search. For example, this remote desktop is used by Windows. Windows computer has remote desktop. If you don't remember port number, you can just Google search for it. For example, when you capture network traffic, when you see the port number 3389, but you don't remember what this port number used for, you can just Google search. You can just either search for ChatGPT or search for Google, like or Bing. Right now I'm using Bing, so I'm not searching Google by default. But in ChatGPT, you can search what does port 3389 used for, and you can immediately find the answer. So used for remote desktop protocol by a proprietary protocol developed by Microsoft. So for some port number, you should memorize by your heart, but for the other port number, you don't need to memorize that. You can just Google search them whenever you see them. Okay, so that's the TCP header, UDP header. They are the two dominant protocol used in the transport layer. In the network layer, the protocol is called IP. The full name is Internet Protocol. The IP header is here. And IP header, normally it has 1, 2, 3, 4, 5 rows. So normally it's also 20 bytes. Remember, each row is 4 bytes. So normally IP header is also 20 bytes. But IP header could be longer than 20 bytes. If some IP packet, they could have some optional field. So that's why it has these several bits to identify what's the length for the header. So the first 4 bits is used to identify what's the version for the IP protocol. Right now, we are all using IP version 4 protocol. So for all the current packet, this part, these 4 bytes, the value is basically 0, 1, 0, 0. So that's indicate. That's indicate version 4. And of course, there are also IP version 6 in use by some country, by some computer. Then the IP version 6 use a very different IP header. Here is 8 bits used for type of service. So when people developed internet protocol, TCP/IP, they envisioned that for different type of service, we should provide different quality of service. Like for some important traffic, we should provide VIP service. For less important traffic, we should provide the common economy service, just like on airplane. But because there is no enforcement in using this type of service field, so every networking program, they want to indicate that their service is VIP. So gradually, eventually, all the internet router, they just ignored the information in the type of service field. So it's not widely used anymore because routers, when they do routing, they just ignore this field. This length is the total length of this packet. So the entire packet is how long. So that's the length here. And these 4 bytes is for fragmentation. Fragmentation, I think I will just skip it. It's a little bit complicated to introduce that. These 8 bits is called time to live. It basically indicates how many hops the packet can go through maximum on internet. Because of the complexity of the internet networking structure, some routers, they may have some misconfiguration. So if you don't have this time to live value, a packet may be transferring in the internet forever because there may be some loops, transferring loops formed in the internet. So a packet could transform in a loop forever on the internet network. So to prevent that kind of problem, every router, when it receives an IP packet, it will reduce this time to live value by 1, then deliver to the next router. The next router will also reduce the time to live value by 1. When this value is reduced to 0, the router will drop this packet, simply drop the packet. So in this way, if you put a time to live value equal to 16, then that means the packet can only be delivered up to 16 hops on the internet, then it will be dropped. So that's the time to live value. These 8 bits is indication of what's the upper layer protocol for this packet. Remember, this is the network layer. The upper layer is transport layer. So most likely the value here indicate this is a TCP packet or this is UDP packet. But in the transport layer, they are not only have TCP UDP, there are some other protocol. So they are indicated by different values. So this is upper layer protocol. Um, if you search, you can find the upper layer field in IP header. For IP version 4 is called protocol field. It's 8-bit identify the type of value. So here are the common values in the upper layer field. Like TCP is value 6, UDP is value 17. But beyond these two protocol, there are many other protocol using this IP, using the network layer service, like ICMP, IGMP. This AH is also like IPsec. It also build directly on top of network layer. It doesn't build on top of TCP, the transport layer. It built directly on top of network layer. So the upper layer is called authentication header. So when you develop an IPsec protocol, you need to use that. And all this is here. So that these are some other protocols. And beyond that, this is a checksum. It's similar to the TCP packet header, that UDP packet header, that checksum is for the receiver to find any bit error in the packet. After that, these are two important information. This is the source IP address. This is the destination IP address. So that is IP addressing. In the TCP header, it has a source port number, destination port number. So how much overhead with TCP packet? So TCP header normally is 20 bytes. The IP packet header is normally 20 bytes. So normally for a packet, for TCP IP-based packet, the majority network application is built on TCP IP. Normally a TCP IP packet, it has 40 bytes overhead plus this application data part. So the overhead is 40 bytes normally. Okay, any questions so far for this IP packet header for the port number service? Okay, IP addressing. In IP addressing, it means that in a local area network, all the local area network, they will be only different by the last few bits. They all common in the first multiple bits. So different subnet, different local area network, they all have a common first multiple bits. So that is called subnet. And this indicate that this network this network has three subnet, has three local area networks. So this is one local area network. This is one local area network. This is one subnet. Remember, IP addressing is addressing of the network interface card. So this is a router. This represents the router. This router, because it has three network interface card, so it has three IP address. Just like your home Wi-Fi router, your home Wi-Fi router has two network interface card. One network interface card connect to the ISP, internet service provider. So that interface has the global IP address assigned to your Wi-Fi router by the ISP. Your Wi-Fi router also has internal network interface card. So that will have an internal IP address. So a Wi-Fi router will have at least 2 IP addresses. An internet router, if the internet router has like 20 network interface link, then it will have 20 unique IP address. So just remember that concept. For your laptop, if your laptop has enabled both the Wi-Fi and Ethernet, then your laptop will have 2 IP address, one with Wi-Fi link, one with Ethernet link. An IP address, this 32-bit IP address, usually we write them out into this 4-byte value. So each byte value is a decimal value. It's between 0 to 255 because each byte is 8 bits. So the value is between 0 to 255. And in internet addressing, it uses so-called CIDR addressing method, is classless inter-domain routing. A subnet is written in this format, a.b.c.d/x, where x is the number of bits in the subnet portion of the address. Like this, open the light. Like this represent that this subnet represent that the first 23 bits it's fixed. So this first 23 bits is called subnet address part. The last 9 bits, remember overall is 32 bits. The last 9 bits belong to the subnet. So any IP address within this subnet, they only differ in the last 9 bits. And when we write out this a.b.c.d/x format, this IP address here is basically the IP address when you zero out all the host part addressing bit. So this that's why this last 1 byte is value 0. This byte is 10000, so that is 16. So that's the subnet. And from this, you can see how big is each subnet. Because each subnet, you can only change IP address in the host bits part. So each subnet, it has this 2 to power 32 minus n IP address. Basically, when the n become bigger, the subnet will become smaller. The biggest subnet in the internet, the value n is equal to 8. So there is no /7/6/5 subnet. The biggest subnet in internet is a /8. The first IP address in the subnet is basically this a.b.c.d. The last address in the subnet is basically you set the rightmost all these bits to be 1, then that is the last IP address in the subnet. Let's use one example to make sure that you understand how do you find the subnet for a company. Suppose a /28 block of address is granted to small organization. We know that one of the address in this organization is this IP address. The question asks you, what is the subnet representation? What is a subnet assigned to this organization? What is the first address in this block? Well, the first address in this block is basically this xy.z.t. So that is the first address. So the main question is find out this first address, find out what's the n here. The n here is already given, is 28. So first, we try to transfer this decimal representation of the address into binary value. But actually, you don't need to transfer every bytes because this is last 28. So that means that only the last byte is affected by the host part, by the subnet part. The first 3 bytes, they do not change. So you don't need to transfer them back to the binary anymore. But in Google, like in Google search engine, you can do the translation very easily from decimal to binary. In addition, there are many websites that they provide this mathematic transformation between different unit, like you can do you can just search binary to decimal and then binary to decimal converter. And Google provide this, and there are many other websites provide this as well. So like if you want to transfer from decimal to binary, if the decimal is 234, and then the binary is this value. If the decimal is this, then the binary is the 100. But remember this, each byte in the address is represent 8 bits. So if this byte in that address is 4, then the 8-bit should be 50 plus 100. So that's how you find the addressing. So basically you do this decimal to binary transfer. Then because this is /28 block, so the bits belonging to the subnet part that can be changed is only the last 4 bits, because 32 minus 28 is last 4 bits. So only the last 4 bits belong to the subnet. The first 28 bits, they are all fixed. So to find the first address in the subnet, you just zero out all the host part for this address. So you zero out the last 4 bytes. Then this is the first IP address in subnet. You transfer them back to the decimal. That's why I said that for the first 3 bytes, you don't need to do this decimal to binary, then to binary to decimal translation anymore, because they are not affected. So you only need to transfer the last 1 byte that is affected by this /28 splitting. And this 100000 its decimal value is 32. So that's the first IP address in the subnet. So the subnet representation is basically the first IP address, then you put /28 under it. So that's the subnet assigned to this small organization. And that's how you find it out. Let me see if we can use the ChatGPT to find out what's the subnet assigned to. What are the subnets assigned to UCF? I don't know if ChatGPT can give me the answer or not. Okay, it seems ChatGPT gave a very good answer here. Let me see. UCF is assigned the IP version 4 addressing of this. This is a /16 subnet. So you can see how many IP address assigned to UCF. is 2 to power 16. That is a 65,000 IP address. 132, 170. But I believe UCF was assigned not only this /16, but also assigned one or two other subnets. This ChatGPT cannot find it out. Oh, it said that UCF employs internal policy and techniques to manage IP address in this subnet. So, so this make UCF network complicated to be accessed by the outside. Okay, any question for this subnet calculation here? So in the first quiz, I will have one question, ask you to do a similar calculation of the subnet addressing as well. Okay, another question in networking is that how does a host get its IP address? You can statically assign an IP address to a host. Usually this is done for a dedicated server. If you set a web server, you usually need to do this. You want to make sure the server has a fixed IP address so that it will be easier for other people to find your server. In Windows computer, you can use this way to set up a static IP address. In Unix computer, you change this configuration file to set up the static IP address. But most computers, or the majority of computers on the internet, they are used by normal users. It's a client computers. They all use this DHCP protocol to try to dynamically obtain the IP address from the ISP. Like in Wi-Fi network, like in your home, when you open up your laptop, when you open your cell phone to connect to your home Wi-Fi, your cell phone, your smartphone will send a so-called DHCP request packet to the Wi-Fi router. The Wi-Fi router will provide this DHCP service. So basically, whenever it receives a DHCP request from your smartphone or your laptop, it will find an unused IP address in its own subnet, then assign that IP address to your smartphone, to your laptop. Then your computing device will use that IP address from that point on for the internet communication. So this is a simple plug and play protocol. So it is very convenient for ordinary user to use, because in this way, you don't need to worry about IP address anymore. The Wi-Fi router, the router provides the DHCP service. It will take care of the IP address assignment. So that's the DHCP service. So every Wi-Fi router, they will provide a DHCP service. And port number, as I said, that there are some well-known port number. So from the internet nonprofit organization, like the whole internet community, the port number between 0 to 1024 cannot be randomly used. It's all reserved for well-known service. So like for the email, for the web, for secure remote connection, all those well-known service, they have a predefined port within this range. And if you want to use any port within this range, you need to to go through the Internet Organization's review, you need to publish your protocol standard to be used for everyone. So this is how this port is managed. But any port number bigger than 1024, they are not managed by the Internet Organization anymore. So you can freely to use those port number. Like the remote desktop protocol developed by Microsoft, it doesn't go through this Internet review, public review process. Is a proprietary protocol from a company, then the company can use whatever protocol bigger than 1024 for its own service. So that 3389 is used by the remote desktop protocol developed by Microsoft. Skype, like a Zoom, they all define their own service port. If you want to know what's the port for the Zoom, you can ask, what is the service port used by Zoom? So you can see, this primary port used by Zoom. Zoom uses this two port for web-based communication. And Zoom uses 8801, 8802 for the client meeting. Like when you open up a Zoom meeting, Zoom client software, it will connect to the Zoom server by using this 8801, 8802 port. And for TCP. For UDP, it will use this port because for video conference in the Zoom, it will actually use UDP protocol instead of TCP protocol. As I said, multimedia application, they usually use UDP protocol. So for multimedia, it will use this for all the audio and video and screen sharing during the Zoom meeting, because they can tolerate data loss, but need to be real time without interrupt. This is used for secure communication, for initial connection, for the TCP-based connections, because you need to still transfer some data communication between your Zoom client and Zoom server. So Zoom software use all these ports. So you can see that all these ports, they are all bigger than 1024. And they can be freely used by the commercial software. And this is also the foundation for firewall rules. Suppose you set up firewall, you don't allow like network games. For example, if you don't allow Fortnite game, which is a very popular shooting game, you don't allow Fortnite program to go through your network, then on your network border gateways firewall, you can set up firewall to block that specific port used by Fortnite. Of course, Fortnite, they have their own way to try to avoid this blocking. So, but that's another story, this blocking and unblocking. But for all those well-defined ports, and you can use firewall rule to set up the filtering rule to block those traffic. And a server always use a fixed port because you want to make sure all the client, they can connect to the server without any problem. Of course, a server can run on a customized port. Then that means that if you run that server, you want to provide service, you need to tell all your client that please connect to me through this newly defined customized port. If you want to avoid blocking by firewall, you should do that. How to decide? This is for network traffic capturing, is how to decide on IP packet direction when you capture traffic. if you see the source port is this well-known service port, then you know that the source computer is a server. If the destination port is those well-known service port, then the destination computer IP address is the server. So you use this way to identify what's the direction for this packet, whether this packet is from the client to the server or whether this packet is from the server to the client. So you use this port number, where the location of this port number to identify the direction for that packet. And IP addressing, how does an ISP get block of addresses? The internet IP address is managed by the Internet Nonprofit Organization. It's called ICANN, Internet Corporation for Assigned Name and Numbers. They allocate address to each country, to each region. Then each country, each region, they have their own review committee to review how to assign address to each smaller region or smaller company. The IP address is public information, so you can actually find the biggest subnet /8 address allocation by Google search to find it. And for example, let's just do search IP version 4 address allocation. List of assigned /8 IP address. And you can see that these are because /8 is the biggest subnet. In IP version 4, there are only 256 /8 subnet. So you can see that why it doesn't assign out to a company anymore, because it only have 256 /8 subnet. But when the internet was first designed in the 1970s, people didn't realize that IP address is a very precious resource. So at that time, the internet community actually assigned out some /8 subnet to some company at that time. Like this 17/8 subnet has been assigned to Apple, because at that time, Apple is one of the leading computing device company in the 1970s. So it was assigned with the 17/8 network. AT&T is a big telecommunication company. It was also assigned with this 12/8 subnet. And Ford 19/8 subnet. Even MIT, because MIT is a major participant in the early stage of the internet design. Remember, internet was designed under the grant by DARPA. So DARPA sponsored several national labs and several universities to develop the TCP/IP protocol. So MIT was also assigned with the /8 subnet. I believe it's 18/8 subnet was assigned to MIT. However, MIT had returned that /8 subnet to the internet community, I believe is after 2010. So it's not early. They only released the ownership for that subnet to the internet community after 2010. But these subnet, they are still owned by this company. So once you assign them out, you cannot get it back. Remember, the internet only have 256 /8 subnet. And these companies have occupied such a big subnet. Remember, a moment ago, I showed that UCF was assigned with a /16 subnet. This Apple company, this subnet is 65,000 times of UCF subnet size. You can see how wasteful of the resource that has been assigned to a single company. But anyway, that's a historical problem. So once people realize that we should not assign /8 to a company, they already assigned many out. And then for the remaining /8 subnet, they begin to assign to a region, like RIPE NCC is basically means this subnet is assigned to Europe. Then in Europe, they have their own nonprofit organization to further assign this /8 subnet to a smaller, like /16 subnet scale to different country and different companies. So you can see all these subnet, they assign to different continent. Like ARIN is a continent for North and South America. APNIC is for Asia, for most Asia countries. And so RIPE is for Europe. And you can see all of them assigned to different continent, and they will further manage them. But before people realize that many /8 has been assigned out, including some commercial company and including, you can see, DoD, DARPA, because internet was originally sponsored by DARPA by design. So at beginning, many address has been assigned to DARPA, to DoD. Once you sign out, you cannot get it back unless DoD released it back to the internet community. But it seems that they never released out. You can see so many /8 is assigned to the DoD. Another point for the IP address is that many websites, they provide the so-called IP address locating service. So basically, it can tell you what's the geolocation for that specific IP address. For example, if you receive data from a specific IP address, you can use this IP address locator service to find out who have sent you that packet. This is IP location. So there are many websites provide this service. IP address location setup check. Like when you connect to this website, it immediately tell you what's the IP address for your computer currently. Because my computer is connecting to UCF campus network. So its IP address is one of the IP address within that /16 subnet assigned to UCF. And it said IP location is in Orlando, Florida, and the ISP is the University of Central Florida. And if you want to find, if I type in an IP address, it will check that this IP address belongs to University of Massachusetts, Amherst. This is where I got my PhD degree. So this is one of the IP address in UMass Computer Science Department. And it can correctly identify where is the geolocation for this IP address, who owns this IP address. So it can tell you all that information. Okay, another important concept in IP addressing and networking is this network address translation. Because we are using network address translation almost everywhere. Whenever you use Wi-Fi, you are using net. Because all the internet Wi-Fi router, they actually provide this NAT service. The purpose for the NAT service is basically people find out the IP address is such a precious resource, and we don't have IP address for every computing device in the world. Because IP version 4 has only 4 billion IP address, but remember, many of them have been wasted in those /8 subnet assignment. And IP address assigned to some other country, they are very, very limited. So how do we solve these IP address precious issues? So people quickly develop this NAT protocol. Basically, we can use a single global IP address to support dozens or even hundreds of computers behind it. So many computers can use and share one single IP address to go to the internet. The basic way is that, suppose this is your home Wi-Fi router. In your home local area network, it uses a so-called private subnet. I will explain what a private subnet means. Basically, it has its own subnet. Then every computer has one IP address within subnet. When the traffic goes through this Wi-Fi router, the IP address will be automatically changed by the NAT protocol service running on here. The basic way for the implementation for NAT is that this Wi-Fi router will maintain a so-called NAT translation table. It's dynamically maintained by this Wi-Fi router device. So suppose one of the internal computers send out a web request. Suppose this web request is to this web server IP address to port 80. So this is HTTP connection request. Then when this packet goes through the router will basically change its source IP address. Original source IP address is this client's private IP address. This IP address will be changed. In addition, the source port will also be changed. And then this changed information will be updated in this NAT translation table. So it basically shows that for one connection, inside, this is IP address and port number. The outside, it should have this global IP address. Remember, this Wi-Fi router only has a single global IP address, but it should have this single IP address and this single port number. Then when this packet goes to the web server, remember, suppose this is a SYN packet, this connection request packet to the server. The server sent back SYN packet. This is the packet sent back by the server. Basically, the source IP address, source port is same as here. The destination IP address, destination port is also exactly the same as here. So from these four values, you know that they belong to the same TCP connection. Remember, TCP connection is uniquely identified by these four values. So these four values, they are same. So you know that they belong to the same TCP connection. Of course, the source and destination reversed because of the direction of the packet reversed. So when this packet arrive at this Wi-Fi router, the Wi-Fi router look up the table and translate the destination IP address and port number back to the line side address and port number. Then when this packet appeared in the local area network, it can arrive at the correct client because this IP address and port number is this source IP address and port number. So they belong to the same TCP connection. It will arrive at this computer without any problem. So that is how you maintain a TCP connection through this NAT device. The NAT device will do this address translation, not only TCP address, but also port number, do the IP address and port number translation dynamically by the Wi-Fi device, and it will maintain this TCP connection. However, this NAT service has one problem, that it only allows TCP connection to be initiated by internal computer. It doesn't allow internet computer to initiate TCP connection to one of the internal computers, because all the internal computers to the outside, they have the same IP address. So from outside point of view, all the internal computer, they looks exactly the same to each other. So there is no TCP connection from the global internet to internal computers that can go through this NAT device. So the motivation is to use just one IP address to support multiple computing devices, which is very successful. The NAT protocol is a very successful design. So then there's no need to allocate a range of IP address anymore from ISP. Another introduced benefit by this NAT is that it is more secure for internal network, because internal computer cannot be connected by the outside computer. Basically, outside computer cannot initiate a connection request to internal computers. So internal computer is undistinguishable to the outside. So this will prevent many attacks from internet, because internal computer is basically invisible to the outside internet. So this will make those internal computers secure, more secure than each one has a global IP address. So that's why UCF actually use this NAT device. UCF border gateway is running a much more complicated NAT service. Of course, for UCF NAT, normally a Wi-Fi router has only a single global IP address, but UCF NAT service has many global IP addresses. Remember, UCF was assigned with the /16 subnet. So for UCF Wi-Fi route, this NAT device, the global IP address that could have tens of thousands global IP address that can be used. So that's why the NAT table should have the one-side IP address as well, because if you have multiple global IP address, they should be recorded in this one-side address column correctly, so you can distinguish them together. For home Wi-Fi, this one side means the wide area network side address. All these IP addresses are actually identical. They only differed by the port number. In your home Wi-Fi router, all the one side address, the IP address is all identical, all equal to the single global IP address. They only differed by this port number. So port number is very, very important. And the port number field has 16 bits. So in theory, a NAT device can support more than 60,000 simultaneous connections with a single global IP address. So that's how good the NAT can be done. But NAT is also controversial, because when NAT was presented, it violated end-to-end argument for the internet design. Internet design in the beginning, one of the principles is that each computer is uniquely identified by its IP address. But when you use the NAT service, all the internal computer, they cannot be identified by the IP address anymore, because from global point of view, they all have the single IP address, so they are not distinguishable. So this violation makes multimedia communication very difficult in the early stage of the internet. Like a P2P file sharing, video conference, web hosting, they all make difficult to do with this NAT device. Private IP subnet used in the net. Internet organization, they define this three subnet as the private subnet. Private subnet just means on the global internet, you will not be able to see any IP address belonging to this three subnet. Because any IP address belonging to these three subnet, they should be used within a private subnet behind the net. They should never appear on the global internet. So UCF uses the 10/8 subnet. And like right now, if I check my computer's IP address, because I'm using Mac, you can use ifconfig. You can see IP address. What? Which one? I don't remember what's the name. Because this one gives too many. Okay, let me. Okay, this is IP address for my computer 10.33. This is IP address assigned to my computer by the Wi-Fi router in the UCF campus network. But when my computer goes out, its IP address is actually, as I showed in the IP location service, IP address is actually 132.170. So when my computer sends data out, originally it has a 10 something as a source IP address, but when the packet goes out of UCF network, the packet will be having this source IP address because of this NAT service make the address translation. And home Wi-Fi router, they usually use this subnet, this private subnet. And actually, most home Wi-Fi router, they either use this /24 subnet or they use this 1.0/24 subnet. Because this /24 subnet has 256 IP address, so that's enough for home use. So most home Wi-Fi router, they use this smaller subnet for easier management. Sorry, I have to work out frequently to enable the light. 127.0.0.1, it's called localhost. Basically, if your networking program send out data to 127.0.0.1, the data will never go out of your computer. It will return back by the network interface card to the operating system. So this is mainly used by inter-process communication, because when you generate network programming, you use TCP/IP for networking communication. But sometimes you want multiple processes running on the same computer to also talk to each other. And if you don't want a different way for your programming, you still use this TCP/IP programming. Then how do you make those multiple processes talk to each other without a packet goes out and come back again? you use this destination IP address 127.0.0.1. So the packet will be delivered from one process to another process. And another problem posed by NAT is that if you want to set up a server behind the NAT, you will have trouble because server need to be directly connected by all the internet client. However, any computer behind the NAT is unreachable by the internet computer. So how can you make internet computer to connect to your web server behind the NAT? To solve that problem, people present this concept called port forwarding in the NAT device. This will enable you to set up a server behind the NAT. And for example, if you want to set up a web server behind your home Wi-Fi router, you can configure your Wi-Fi routers, these firewall rules, to enable a so-called port forwarding. Basically, if your Wi-Fi router receive any incoming packet that has the destination port 80 or 443, you change the destination IP address to the internal IP address of your web server. So that means internally you can only have one web server. You cannot have two internal web servers. You can only have one internal web server. For all the incoming web request traffic, you always forward to a prefixed internal IP address. So the internal web server, you should have a prefixed IP address beforehand, a static IP address. And if you set up an internal SSH server, then for any incoming packet that has the destination port 20, you change this packet to be the destination IP address to be equal to that SSH server. So this is basically port forwarding means that you poke a few holes on your firewall. So for incoming traffic, satisfy that rule in a hole, you let it go through that hole to the specific server inside. This is a figure I copied from Wikipedia. Yeah, so suppose within your Wi-Fi network, you have a SSH server, you have a web server. Then for incoming connection request that have this port number, because this port is port 80, then this packet will be allowed to come in and it will make the translation. The destination IP address will become this IP address. No, destination IP address will become this IP address, and port number does not change. So the packet will be forwarded to this specific internal computers. So, but as I said, this is one weakness for port forwarding. You can only set up one server for a given service on a fixed port. If you want to set up two web servers, then one of the web server must use a self-defined port. For example, port 8080 or port 8000, so that these two servers will be distinguishable by the port number. Okay, any question for the port forwarding concept here? Okay, the last concept I want to review is Internet Control Message Protocol, ICMP protocol. ICMP is in the equivalent role as TCP and UDP. So you can think that it's a transport layer protocol. So it is built on top of the network layer. It is built on top of the IP protocol. So in IP packet, the upper layer field should have the value indicate that this is an ICMP packet. So ICMP is mainly for internet control. So it's mainly for diagnosis of the network. In the early stage of internet, the network is very unreliable. the router is unreliable, the internet link, the Ethernet line or other lines, they are not reliable. They could be broken frequently. So people run a lot of this ICMP traffic to diagnose the network link to find which link has broken, which routing path the packet goes through. So for all those, they use this ICMP packet. Nowadays, we mainly use this three type of ICMP packet. So in the original definition of ICMP, it defined so many different type of ICMP message. So for each ICMP packet, it has two value fields. One is type, another is code. And type 3 represent the network conditions. A different code represent different error situation for the network condition. Type 11 means the TTL expires. So if a packet TTL value becomes 0, the packet will be dropped. Then the router will send this ICMP packet back to the original sender of that dropped packet. So you can see what's the reason for this ICMP protocol. It tries to make sure the router can inform the sender or receiver something wrong in your network translation. So this one is used by itself, and echo reply and echo request, they usually used by pair. So this is echo request, this is echo reply, this is echo request. So right now, all the network printer, they use a lot of this echo request and echo reply. Network printer use it to tell all the remote computers that I'm online. So it frequently ping. And if you want to find if a network printer is working, is online, your computer also send out echo request message to that network printer's address. So ping is used a lot by the networking printers. This TTL expire, this error message is used a lot by another program called traceroute program. The traceroute program is basically try to trace the routing path for a packet. Suppose you send the data to google.com, but Google have actually set up many servers all around the US, all around the world. How do you know which server provide the service replied to your Google's connections? How do you find out that? You can use traceroute to find it out. So traceroute, basically, when you run traceroute from your computer to a specific destination, the traceroute program will send out 3 packets. Each packet will have TTL value only equal to 1. Then these 3 packets will be dropped by the first hop, because the first hop, once it receives that packet, it will reduce TTL value by 1. When TTL value becomes 0, then the packet will be dropped. This router will send back, the router will basically send back this type 11 code 0 ICMP packet. Then the traceroute program will receive these 3 ICMP packet. Because each packet is sent back instantaneously by the router, so you know what's the round trip time between your computer and the first hop. The traceroute sends 3 probe because it wants to know what's the average round trip time. Because network condition could be changed very quickly. If you only get 1 round trip time value, it may not be accurate. So traceroute sends 3 times. Now from this 3 times, it can calculate what's the average round trip time between myself and the first hop. After that, it sends another 3 probe. in this time, the 3 port will have TTL value equal to 2. So the packet will be dropped by the second hop. The second router will send ICMP, a TTL value expired message to the sender. So it will receive the response, then it will know what's the round trip time to the second router. It also know what's the router's IP address because this packet, ICMP packet is sent back by the router. So you know what's the source IP address of the router. Then you just do this iteratively until the packet has received by the destination. You finish all the trace route. So in this way, you not only know what's the round trip time between myself and the first, second, third hop, but I also know what's the IP address for each router here. Then you can figure out what's the actual physical path for your packet to transmit through between your computer and the remote destination computer. This is one example. I will show another example. This example I did in my home because I cannot do traceroute here in UCF because UCF border gateway will actually block ICMP packet. So even if a router send back a TTL value expired ICMP packet, the router will block it. So I will not receive the response. So if I do traceroute from my computer, it's called a trace route. Suppose I do google.com and it's so small. How do I? How do I make it bigger? Oh, bigger. Okay. Okay, you can see that I use traceroute Google, and the first several hops I got the response time, the 3 round trip time. So you know what's the hop's IP address, what's the 3 round trip time, and these routers they all have 10 something, so they are all internal routers, and this is also internal routers. It has respond back, but from hop 10, it become star. So this means that I don't get any IP address. Oh, I think okay, it's interesting. I think from this year, the UCF gateway does not block ICMP packet anymore because I can get response from this global IP address and the round trip time without any problem. Some router, I don't get response. It basically because that router does not generate this ICMP error message out. So I don't get any answer because some routers, they may not implement this ICMP protocol and they will not generate this response. Okay, previous years when I try it, all the following hops, they all star means I don't get any response. But this year seems it works. And many times, many internet router, they actually have a global DNS. They all actually have a domain name. That traceroute will also try to get what's the domain name for that router's IP address. Then from this domain name, you can basically figure out where this router is. For example, this one, when I traceroute to Google, it showed this is my router's name, and this is BS Bright House Network. Well, this screenshot is several years, probably 5 years ago. So at that time, my ISP is still Bright House Network. It's not merged yet. So it's Bright House Network. Then this is Orlando level 3. Orlando level 3. This is Miami, Miami. So you can see that the Google server actually in the Miami area. And this is another example when I trace route to my to the Chinese college where I got my bachelor degree. And this is that university's website. And you can see this round trip time. Here, there is a big jump from 80 to 300. This is because this is across Pacific Ocean. So because when the cable goes through Pacific Ocean, the light speed propagation will become seeable. So this is a propagation delay due to this long distance. And after that, it's all bigger than 300 milliseconds because that's a lower bound for propagation. So you cannot go below than 300 milliseconds for that long distance. And from this router's name, you can also figure out where this router is. This is Orlando. This is Roadrunner because at that time my ISP is Roadrunner service. CFL, Central Florida, Orlando, and this is Dallas. So basically from Orlando to Dallas, then Dallas to Los Angeles. Then this is the last hop inside US. So this is edge router in Los Angeles. Then this is the first hop in China, and it has a China netco. So that's the biggest ISP in China. It's so from this name, you know that this is a router between China and Los Angeles. After that, these are all the router inside China. But this router, they don't have a domain name. They only have IP address. So and overall, it travels through 17 hops and trace complete. Trace route can run up to 32 hops. If it still have not reached the destination, it can run up to 32 hops. And you can actually try trace route from some online website. Many online websites, they provide this trace route function. So you can do trace route from those web server to a destination. Of course, that's not from your computer. You are doing trace route from those web server. And you can check them as well. Okay, that's all for the basic networking knowledge. And I will release a quiz in next week, next Monday. That quiz is about the basic networking knowledge. Okay, that's all for today's class, and see you next Monday. Remember, you need to finish this academic activity assignment by the end of this week for the financial aid purpose. Okay, that's all, and see you next Monday.
Thank you.
Thank you.